Okay, this is the next part of relativity. This is where it starts to get a bit weird. First of all, we have to know not only what is meant by a frame of reference, but what is meant by an inertial frame of reference. Well, you know what an inertial body is. It's basically not accelerating. It has the same inertia. So a frame of reference, which is a set of axes in which you take measurements, which does not accelerate. So sometimes they ask for a frame of reference, sometimes they ask for an inertial frame of reference. If it's inertial, it does not accelerate. One interesting thing is that the rules of physics should work equally in all inertial frames of references. But it appears that some aspects of electromagnetic radiation, electromagnetism, does not seem to work properly. And this was a little bit of a problem. You could look at this website, which has an interesting discussion about why electromagnetism doesn't work quite properly. But we're not going to go into the details of this. You can do this if you have time. But let's just say that Maxwell and others basically saw that this idea that all inertial frame of references work the same didn't work with electromagnetism. And as we know, electromagnetism or electromagnetic waves is to do with light. So light itself is a core problem to this idea that all inertial frames of references have the same physics. Maxwell kind of figured that when you have two electrons which are moving parallel to each other, there were certain asymmetries. When they were static, there would be just one repulsive force between them. When they were moving, because one is removing relative to another, there will be another force, which is Maxwell's force, because of moving charges. And this unbalance of this asymmetry did not work for Maxwell. And eventually it was solved by a young man called Einstein, who wrote a paper called On the Electrodynamics of Moving Bodies. On the Electrodynamics of Moving Bodies. We know this paper today as the special theory of relativity. So what we're going to do is look at the two postulates of the special theory of relativity. The first postulate, that laws of physics are the same in all inertial frames of reference. This is the first postulate. In other words, there's no experiment, there's no possible experiment you can do that can determine if you are moving or if somebody else is moving relative to them. In other words, all motion is relative. The second postulate, and this is where it starts getting really, really weird. The speed of light is the same no matter what the speed of the source or the observer is going. So in all inertial frame of references, everybody must agree on the speed of light. And this has really disturbing consequences. So basically, the speed of light is basically a law of physics. Maxwell said this, that the speed of light has an absolute value. Maxwell figured out that the speed of light is equal to 1 divided by the root of mu epsilon. Mu is a constant which tells you about the magnetic qualities of the medium. Epsilon is a constant which tells you about the electrostatic properties of a medium. So the speed of light just depends on these two constants. It doesn't depend on the velocity. These are constants in all frames of reference, and so c will be a constant for everybody. This has disturbing consequences. Let's take this example. We know from this postulate that c, the speed of light, is absolute. Time is not, distance is not. We find the speed of this light beam as it goes from here. What is the speed? Well, it's just the distance divided by the time. Let's do that again. Here we go. If I want to measure this speed, it's that distance divided by that time. That's straightforward enough. But what happens if the bike is moving? What will the speed of light be then? Now, relative to the bike, the speed is still the same. It moves the same distance in the same time. Relative to the static observer, relative to the bike, Now the distance has gone further. It started here and it ended up here. So, and in the same time, this means that that light has travelled faster. It's gone a bigger distance in the same time. This cannot happen. So we will not agree. So the only way we know that the speed of light must be constant, both observers must measure the speed of light of constant, which means either we don't agree on distance, or we don't agree on time, or we don't agree on both. The problem is that the speed of light is different for different observers. Now, basically, the way it appears is that since the light travels twice the distance, it must obviously take twice as much time for us to have the same value for the speed. And this is where it starts getting completely weird. So what we have here instead is that the cyclist is moving like this. Now, we measure that same distance in the same time as before, but for the cyclist, it only travels a certain distance like this, which means his distance is going to be shorter and his clock is going to be slower. It's only a small amount of time. So here again, we don't agree on distance, we don't agree on time, because this is what is going to happen in this time frame. We cannot agree on time. And this is the thing, is that his clock will be going slower than mine. So basically, one thing you remember is that moving clocks go slow. Another thing is, if the time is going to be less, the distance must be less as well, which means the lengths are going to be less. So an object that is moving in another frame of reference is going to get shorter in the direction that it's moving. So here we go again. So we don't agree on lengths either. And we have this factor called length contraction. So to summarize, the speed of light is the same as measured by all observers in all frames of reference. Maxwell knew that from his equation C is equal to 1 over epsilon naught mu naught, or the root of those. The distance and time, or measurements of distance and time, depends on your frames of reference. So there can be disagreement between different observers in different frames of reference on what time is and what distance is. But not only distance and time, it also works out that you will not agree on velocity, you will not agree on mass, you will not agree on energy. All these depend on your frame of reference. And only light in a vacuum is constant. This is the introduction to special theory of relativity.